So I'm just creating the bill of materials for my schematic that I did on the last live stream. How you doing? Welcome to the screen. Basically doing the PCB design for the Bluetooth and the IMU. Right now I just need to get together my bill of materials. So I basically what I've done is added some manufacturing part numbers and JLC part number to the bill of materials in KiCAD. I think this will be easier to manage when I export it out and finally get this assembled. Obviously I've got quite a few components to go, but it shouldn't be that long. It's a bit of a ball ache really. How are you guys doing today anyway? Eight picofarad capacitor. Done that one. Let's go find the MIC 5205, which is C379. Where's that? So that's a 3v3 regulator. This should make it very easy for me to basically generate my bill of materials when it comes to it, which shouldn't be that long anyway now. So USB, so it's the USB protection IC with very low capacitance. .7 nanohenry inductor. Need to make sure I tick off anything that I don't want to populate. So that one there. Don't want to populate any of this. Do want to nope, don't want to populate that as well. So 2.7 nanohenry inductors done. There's a few more ports to go, but we're getting there. So low pass filter is RF1 or filter 1. We'll need to make a footprint for that part. 0.8 picofarads. 0.8 picofarads, that's this one here. I should have really used this from the start. It would have been a lot simpler. Then I have a 0.3 picofarad, which is this capacitor over here. We'll need to basically do a check on all of these components afterwards. But I'll do that after a slide switch. I don't need a slide switch. I can delete that. And then I've got a bunch of resistors. I've tried to keep them to as low count as I could. You can see I've got some 10Ks. We'll get rid of that. And then I have some 5K11 resistors. Just this one there. It's not too many to go now. How are you guys doing anyway? I've got few viewers. Don't get many usually. If you have some feedback for me on my Art of Electronics videos, that would be great. Some 1K resistors. Right, and then I've got a 10 microhenry inductor, which is this one down here. Should be a 0805, which it is. Only a few more ports to go, and then we can do some fun bits afterwards. So this is a 10 nanohenry inductor. Then we have a 2.7 nanohenry inductor, which I have already done. So just mark that off. Oh, basically all I'm doing, I know you can't see my second screen, but I'm just transferring my bill of materials over to KiCAD so I can export it out a little bit easier, and basically so there's no mistakes afterwards. I've only got 3 more components left to do, and then I will be able to go on to do the footprints for some of the components that don't have a footprint at the moment. Such as the antenna and the filter, I think. So I think those are the 2 main ones that don't have footprints right now. If there's anything specific you guys want me to look at as well, just let me know. So there's one more to go now. How exciting. So just looking at that part, it's the switch. Where's the switch? It's down here. And that has a part number, which is this one. You can see I've got test points, which is going to be do not populate. Just going to put down NA in there. So you can see I've got everything all on here. Got all the components that I don't want to be populated marked off. I need to get a footprint for this one and a footprint for this one. I think everything else looks okay. So let's save that and just make sure it's all okay. Means I can close my bill of materials as well. I am going to go through a art of electronics video as well afterwards. I mean, the next question that I need to do is quite simple, so that should be okay. Let's see if I can find a chip antenna on this. It would be ideal if I don't have to design my own. So we got RF antenna. I will need to get rid of the pin count because the antenna that I have selected, just show you. It's basically this one over here, and that antenna has basically 6 pads underneath. I'm not sure if there's any available on KiCAD that I can use as a pre-existing one. It would be good if there is. So let's see. So antenna, and then over here I had got a used one, 2nd edition. I mean, I've not read the 2nd edition one. Sounds good. Is it changed much? I mean, I'm guessing the questions are all different, so the art of electronics exercise doesn't probably help that much. I will just need to design these components myself. So let's do that first of all. So recommended LAN pattern, you can see that down here. I'm going to move that to the side. Go into KiCAD and open PCB or footprint editor, sorry. Are you learning as a hobby, or is that for university or something like that? So file, new footprint. Give it the name of the part number. And what I'll do for now is just move this out the way. You can see I need 4 pads. I think some of the pads are overlapping. You can see there's a feed point just off screen here. just pad 4, and then you've got your radiator, basically pin 1 here, and then these are just pads to hold it in place. So 2, 3, and 5, 6. Not doing much. Do you do pure software or is it embedded? I can see it'd be quite useful for embedded. It's a good skill to have anyway. It's quite fun to learn electronics. So pad X size, so what's that? 1.6 minus 0.9 and 0.7. Well, let's put that in brackets, divide by 2. That should give us the pad size for this, if my maths is not wrong. And the height of that pad is 0.8. So a little bit late over here as well, Mini. It's 11 o'clock. I'm just finishing off, well, getting ready for the PCB design. I need to create a few footprints. So just doing that basically. So 0.8 minus 0.21 divided by 2. Don't need the equal sign there. So it's can you give multiple pin numbers over here? You probably can. Just gonna call it 2 and 5, 6. I'll call it 5 for now. And then what I need to do is make sure I get my spacing right. So if I look at this, I've got 0.9 between the two pads. So minus 0.45. Minus 0.45 and 0.4, 0.4. As far as I can tell. I quite like doing embedded, to be honest. I need Excel here to get the bloody... I don't know why they just don't give pad positions on here. It would be so much easier. But we'll need to calculate the XY locations. So 1.6. Hopefully you guys can see that. So 1.6 minus 0.9. So pad size for 1 and pad size for 4 is this divided by 2, and the X and the Y is 0.8 equals this divided by 2 and 0.8 over here. You can see the space location they do like to make it tricky. I hate doing this. The location X and Y is for pad 1, which I'm calling on this side over here, is 0.9 equals 0.9 divided by 2 So that gets us to here, and then plus this divided by 2, which I think gets us to the center of this pad. So that's the X location. And pad 4 will be just that times -1, and the Y location is just 0. Let's put that in. Six, 2, 5, and 0. 0.625 and 0. Okay, now let's do these two pads. So you've got 0.21 in between. Oh, so the full size is 0.8, and the gap is 0.21. So the pad size, total pad size is this dot. Right, so let me get rid of these calculations first. So you got the total pad size of these two components is, oh, it's not 0.8, it's 0.73 over here. So it's this divided by, nope, X is 0.6, 0.6, and the Y is this divided by 2. Zero 0.6 and 0.26. I think I did something wrong last time then. Let me know if I'm making a mistake on this. It's quite late here. Now the location for that is going to be, on the X is 0 and 0, and on the Y is 0.21 plus the Y size divided by 2, so 0.34 plus and minus. So 0 on the 0.34. I think that looks okay. I can obviously double check everything. So that should be 0.21. Oh, for fuck's sake. Sorry about language. So that's 0.21. That's not right. I'm going to move this to the other side. So you got 0.21 in the middle. Got 0.731 as the big size. So one minus the other. The X is 0.6. That's fine. The Y is this minus this divided by 2. So 0.21 plus 0.26, 0.34. I think it should be 0.21 divided by 2. 0.235. Well, if it's 1 a.m., you don't want to be doing any maths. Okay, yeah, got that size correct. We've got 0.9 there. Just double check that size. So we've got 0.9 Double check this side, should be 1.6. Yep, 1.6. That, let's move this out the way. From there to there should be 0.73. Yep, and then 1.6 and 0.8. So 0.8, 1.6. I think that looks alright now. So I want to make that minus 1.6 divided by 2. Minus 0.4, 2.4. Just might need to move it up a little bit, but let me just draw the box first. Just add a bit of clearance on that. And a pin 1 indicator. And that should be okay. I don't know, KiCAD's been doing it a little bit differently recently. Did you find any? I could go for this triangle shape, keep it consistent with everything else. Let's see. I was gonna do the charging stuff on this, but decided against it afterwards. I think because I need to get this out quite soon. I forgot to set my library. It's like I'll just do another board afterwards to test that individually. So TDK and 0. Let me assign that. So footprint assignment tool. Go to my library down here somewhere. Zero. So okay. And then we have one more component to go. I mean, this doesn't have any pin numbers or anything, so it's going to be a bit tricky anyway, but I might need to change that symbol. I'm not sure how it works. Let's go pin 1. So 1 needs to go to the driver or the feed point. So 1 should go to 4. I better change that. So I'm not sure if I can change it here, but I think that's because you have to get them balanced and everything, don't you? If you don't have them balanced, I think some cells can overcharge and some over discharge and stuff like that. Might make my antenna symbol as well, because my feed point on the symbol. So pin 1 is the radiator, so I want pin 4 to be pin 1. I don't want to make this too complicated, but I think that might just work. So pin 1 will be where my feed point connects, and then this is the radiator, but I want that connected to the radiator. Yep, that looks okay. Do you even need two cells at that point? Can you parallel them up and go for a boost converter or something afterwards? The next thing I need is the filter. So that's this one down here. So I need to find the datasheet first. What voltage are you trying to get? Oh, gotta do the same calculations again. Is that the same size? I think that's the same size. No, you can get these. I'm not sure if they do buck and boost together or not, but you can get like multiple converters in one chip. But they're probably all just bucks in there or all boosts in there, I'm not sure. Okay. So PCB editor, I need to make another, not the PCB editor, sorry, the footprint editor. Go down to my, wait, let me copy this first. Go down to my library, wherever that is. New footprint. So DLF 16250 LT 5028A1. I'm just going to reference back to my schematic a little bit. So 1 is in, 3 is out. 1 and 3, so that makes sense. So change that to pin 1. Change that to pin 4. Nope. Change that to pin 3. Two is fine. Change that to 4. Oh yeah, balancer, protection and charging. all three, I guess. But oh yeah, well, charging and balance is probably going to be in one, isn't it? So 0.22 thickness on this. So it's not quite the same part. I shouldn't have deleted my calculations because I could have used them again. Why are you up so late today? Just weekend? We've got to do more maths on this, which is fun. Got 0.45 on this. Got 0.7 pads actually, so I was looking at the wrong thing before. 0.7. Ah, okay. 215. 0.275. I should get the Discord chat running. That would be good. So 0.25 plus 0.45. So 0.95. Just it's slightly out. I'll need Excel again. 0.25. 0.45 and 0.25 as the separation. 0.95. 0.95 is separation. So the XY location or the X location is 0.95 divided by 2. 0.275 is this divided by 2. So that is that plus that 0.6125. And then that should give me the separation I need. 0.95. Yep, 0.95. Yeah, I mean, if you want to look at the BQ, what was it? 25978. We can have a look. Just need to, I think, only got two things left to do on this really. Is creating these footprints, double checking my bill of materials back into that a later time. I'm sure nobody wants to see that on stream. And basically make a start on the PCB design, which I've kind of already done anyway, but I need to calculate the track thicknesses and things for the impedance requirements, because I've got USB on this and I've also got the RF, the 50 ohms for the Bluetooth. So now I'm getting conflicting numbers. So KiCAD calculator says something different from GLC PCB calculator. So I just need to get them to marry up. USB should be fine. I mean, like the size of my board isn't that big anyway. Because I'm making it as a video, I want to try and do it a little bit more professionally, I guess. Got separation. That is not the separation, so that is the total size. The separation is 0.21. The pad size is 0.245. I think that gives me 0.2275. Let's try it. 0.2275. No, I don't know why they just don't give us a table with the XYs. I got the size wrong. Yep, the size is wrong. Yeah, I can. Just give us 1 second. 0.21. So that's done. Let me assign that. So for print assignment tool, my library, and that should be the DLF. Okay, so the PCB design, well, when I say I've made a start, I've done the outline, and I just did that for the video I did today. 3 errors, no net found. Those switches don't look correct. I might need to update that. You can see how similar these are. I'm not sure if there's like, is there quite a bit of a delay on the stream, or is it basically the same time as I'm showing this? But like the PCB is on the screen now. Hopefully you can see it. Oh, I'm just gonna check the dimensions on this push switch. This is approximately the right one. I think I'll need to create this part again as well. That's 6.8. Yep, that's the right size. I mean, yeah, that's my PCB, or roughly the size of my PCB. Got a bunch of different things on there. Got the IMU, which is down here. Let me turn off the useless layers on this board setup. Don't need all of this. Okay, and board setup again. Change it to, I need a 4-layer board. Impedance control, that's all fine. It doesn't really do anything anyway. So where's the rat nest? There you go. There are still a few more components that I need to build up, actually. So when I say few more, two more. I'm gonna have this as an edge mounted connector, so it's gonna hang off vertically from here, where the pads basically, so half the pads will go on top and the other half will go on the bottom of the board. That grid is terrible. Let me change the grid. Should be okay. Anyway, I'm not going to do the PCB design today then. Well, maybe later. The 5 volts. Got the 3 volts. Now I'll start doing it after I've done my switch and everything. What's this part number here? This is the right switch, I think. Oh, that 3D printed. Well, so what it is, I'm not sure if this will have the 3D model for it. It doesn't. The ST link basically comes with that 20 pin connector. So this picture, so you got this connector, hopefully you can see that. I don't want to cut the cable up or anything, and because this is only a dev board, basically what I'm going to do is the I guess the socket for this connector, I'm going to put it like, as you can see on this board here. So I'm going to mount it like this, coming off the board. So yeah, this is a good example. So I'm going to mount it exactly like this. So then I can plug into it from the edge. So it won't take that much room on the board itself. And I don't have to cut the cable. So if I need to do something different with the cable later on, then I can do so. Would that actually plug into the ST link? Oh, I've got the ST link here. How does that work? Oh, I thought it was ST link. It's a nuclear board. Got some nice development boards. I would love to do that. Let's lose something with it at some point. I guess this plugs into the ST-Link. Sorry, it might get a bit loud because I'm looking for the ST-Link. Yeah, I've got the ST-Link in my hand right now. I'm not sure how that would plug into it. Oh, I see. So yeah, it directly plugs into it. Yeah, okay, got it. So you got the male headers on the ST-Link itself, because I've got it with the actual cable plugged in. Yeah, I've got ST-Link V2. Yeah, but it had the cable plugged in. But yeah, once you remove the cable, that red piece, section here plugs right into the ST-Link. I might get that for future. Or I might just actually order a PCB like that. It's probably cheaper nowadays. The problem with Mauser is bloody shipping cost. Like 20 pounds handling or something. If I'm putting another order in, yeah, I can do. I mean, yeah, that looks like it would work. It's only 427. Yeah, when I'm placing a big order, I can order that as well. That's good to know. Okay, oh, I don't like that. Why is it gone? Oh, because I pressed do not populate. Okay, I've done that by mistake. Let me go and fix that really quickly. So generate bill of materials, edit. I want to go to my test points, untick the do not populate. What I want to do is have it not shown on the bill of materials. So I added basically loads of random test points. Well, not random, but useful test points on the schematic to help debug this thing. Yeah, I'm trying to use it as close as possible to Altium, I guess, because the workflow in KiCAD is a little bit weird in that the way you do things, I think, because like you can put down a component, but that component won't have what do you call it? It won't have a footprint assigned to it, or it won't have a part number or anything like that. Whereas in Altium, you know, each component you put down is basically assigned a manufacturer, things like that from the start, which is so much better because then you've already, you know, you have to do that first before you put the component down. Whereas in here, you do your schematic, then you can go into your bill of materials and you can assign your manufacturer part numbers and things like that separately. You're using huge test points. My test points aren't that big, but I guess it's like a pad size 1 mil. There are quite a few of them there. I might move them to the other layer, which probably a little bit better on the other side. Keystone 5000. Oh, I see. Yep. I was just gonna probe onto the pads really, rather than putting something physical on the board itself. But yeah, those things would make it a lot easier to. Yeah, quite big there. Hopefully I don't need to do too much debugging. Oh, that reminds me, this connector's wrong as well. Yeah, makes sense. No, I've not put it. I've put them. I mean, I don't have many data lines on this. It's just quite simple board, really. Quite a few non-connect parts. I mean, I do need to change that. Right, what should I do next? Let's find the USB-C connector. Yeah, the battery. That would be cool. Just gonna check this. Yep, that's the right part number. Don't need that anymore. There we go. Right, let's have a quick look. I mean, I can add some. I've got quite a bit of space. I might be able to add some connection over here for battery charging, but Again, it's going to get a little bit too complicated for how fast I need this, and I really didn't want to do the research at the moment. Two 25887 MP 2672 26887. Oh, USB filter. It's the one I've used in the past quite a lot. It's by ST Microelectronics. USB LC6. I think it's good enough for USB 2.0. ECMFO2. This has probably got lower capacitance than... Oh no, this is something very different. What is it? Has it actually got power line protection as well? No, it's not. So it's a little bit different. It's a filter. Because this is more power protection rather than a filter. Yeah, it's just the ESD. I thought the part you linked was ESD, but no, this is more of a common mode choke filter kind of thing. I guess it's got some built-in ESD protection in there. I mean, it's rated to the right voltages. That's what you need. Thank you, Mehmet. Mehmet, am I pronouncing that correctly? Ooh, need that page. Which part are you considering at the moment? Two 25887. It's quite a neat part though. I do like it. It's not your typical TP4056 inefficient thing. Has it got internal detection for overcharge and over discharge and current and stuff like that? I mean, yeah, it's got the switches integrated into it, so that's quite good. And also on the high side. Have you tested this out yet, or is it just something you're researching at the moment? Oh, okay, that's cool. Let me know how it goes. Seems like it. I think you need a microcontroller and everything. I don't. Is it absolute must-have to have a microcontroller, or is it like a nice to have? The audio amplifier I did recently, you could connect up a microcontroller, but it didn't really need one. See the last bit of your text because of the bloody love port thing and the way. Do you order the ports from LCS and I'm not sure what that says. And let GLC. Oh yeah, so in this board I will be doing it that way because JLC are gonna sponsor that video when I actually do it. So the PCB video is gonna be sponsored by them. So yeah, all the parts and the assembly will be done by them. This is one of the reasons why I want to not spend too much time doing research on other stuff as well. It was a nice opportune time because I was going to design an IMU Bluetooth board anyway. So I was like, yep, if they came to me with an offer for sponsored video. So it's like, yeah, let's go for it. I've ordered the boards a few times in the past. They've always been good quality, to be honest. And I'm not just saying that as well. I think that the support is quite nice. No, they all have massive costs, to be honest. In UK, yeah. When I used to work for a company, a small company in Leicester, and basically it was like the tooling cost was like £200 to get something assembled. Is crazy. And then we started using this company called Osh Park afterwards. They were a little bit better. Well, they were actually a lot better. They were the American company. They made purple PCBs, which was quite cool at the time. I'm not sure how popular they are nowadays, but I think they still exist. If you are looking for an American company, they do exist. They're not the most expensive, but they're not as cheap as GLC, or they're not as fast. I'm just messing around now with this, but yeah. It's like the most unprofessional thing I've ever done. What is that? Ah, okay. So you don't really care, to be honest. Yeah, it doesn't matter. When GLC are so good, then there's quite a few companies based in China as well that offer similar service to GLC. Sorry, I'll need to tidy that up at some point. I'll tidy that up later. Let's leave it as it is for now. It is very sketchy. But I mean, to be honest, I'm just being a bit lazy. I could do it properly with the proper dimensions and everything. Yeah, just can't be bothered right now. I think that's a little bit unfair on KiCAD. Where's my library? When for a free software, you can't go wrong. KiCAD does have a 3D viewer. And I really do like the Altium colors, and I tried to, when I used to use this, like, I think I started with KiCAD 4 back in the day, and I tried to make the colors match with Altium because that's what I was used to. But like my current job, we just use Altium anyway, so I'm so much more used to Altium than this. You had 3D models in there. What's going on? We had Eagle, and ORCAD, I think it was called, in university. Not that I remember any of it. Right, one more symbol to go. I couldn't find the 3D models. I believe they're in here, but yeah, it's disappeared for some reason. And let me try this. Where's the 3D model for this? It's actually in program files. Yeah, that's completely the wrong one. Just need something approximately right. Or I'll just go find the 3D model for it afterwards. And the one that I had before was correct. Or almost correct. Well, this is just annoying, so I'm going to leave that for now. Let's just make sure. Oh, that looks alright. It won't have the 3D models for it right now, but I'll need to go find them and I can add them on later. So only got one more part to go. This is like the most time consuming bit, really. That's why I'm doing it on live stream rather than a video, because I don't think anyone wants to watch a video of someone designing a footprint like that. Well, someone might, never know. Yeah, you do have to check them. I've downloaded them a few times, but yeah, I don't know. Never quite get on with it. .5. That's 3.5. Say that's the edge. Click F-fab. Zero, zero. It's a 20-way header, so 2.54. On a IDC connector, does it go pins 1, 2? Snap EDA. Yeah, I'll need to try that. 2.5. The header itself, the pin is, what's the thickness of the pin? 0.64. So if I make that 1, that should be all right. And it's what? 3.5. So 11, 11, 3.5 divided by 2, 1.75. So that's the halfway mark, 1.75. Five. All right, good night. Thanks for joining today. Hope you get some sleep, man. Crashed on me. Oh no. Still got 2 viewers. How are you guys? Quietly watching in the background. The software's just crashed on me, so we'll have to wait for that to come back. You know what I'll do? Let's go on to the next thing, which I had planned for today. I think I just uploaded this one. So that was the bandpass filter. No, this was what was the last video? It was a bandpass filter. So let's make our next video for auto electronics. Close that, don't need that. Right. So auto electronics, not that one. Open this one. Exercise 1.43, I think we're on now. And this exercise, just open the book. Sketch the, I don't know what you would call this circuit. So diode limiter maybe. So exercise 1.43. Sketch the output for the circuit shown in figure 1.138. So the figure shown in 1.138, let's see if we can actually find those symbols. File, save as. Right, component. Multi-spice is all changed now. I'm not sure if LT Spice has a symbol for a transformer or a coupled inductor, so I think we'll just have to ignore that part. We'll basically put a power supply down, and in the question we have a cable that goes from, let's say, down there, and we have a diode that goes up, and we have a diode that goes down. We have a resistor, and the voltage over here is 6.3 volts, but it's not DC, it's a sine wave, so it's 0 and 6.3. Let's just give it 50 hertz. And the resistor value is 1 kilo ohm, I think. So this is basically the circuit that we have on the question. And we are asked to sketch the output for this. And it's fairly easy, isn't it? So to sketch, I guess let's kind of analyze what's happening. There's kind of 4 states in this circuit. So you look at a voltage of positive less than 0.7 volts. So where the diode hasn't activated, obviously, you got this diode in forward conduction. So you, before 0.7 volts, you've got very little current going down this path. And then after 0.7, your current through the diode starts to ramp up. So most of your voltage drop is going to be across the resistor. So with very little current going through this resistor, there won't be a lot of voltage drop. So below 0.7, most of your output voltage is going to be on Vout. And then when this voltage is negative, or when it's going negative, this diode will be in forward conduction, and a similar thing will be happening. So this basically will be limited to plus or minus 0.7 volts. Oh, well, that is just limited to ground. Oh well, close enough. I mean, these are, as you change the diode, if you went for like Schottky diode or something, it's going to be slightly different than having a normal diode. But what I need to do is basically take this model, I think the best way to explain this is with separate circuits where you have positive direction, where you remove this diode as it's not doing anything in an ideal case, and then you have negative voltage, and for the negative voltage, what I need to do, go back to LTSpice and delete this where that diode isn't doing anything. So you've got negative voltage here, so you've got forward conduction on this diode. So tools, copy that to image, and I think that's the slides for my next video then. I think what I'll do is actually build up a circuit as well, because I've got all the parts that I need for this. Let's call it high. I think that's going to be better for the explanation. So call this high potential and call that low potential. Right, let's go to the image picture format, color correction, set transparent color, get rid of that. Picture format, color correction, set transparent color. Okay, nice and neat. Well, that was one of the easy exercises. So that's really good. Should be a fairly quick video. And I'll basically try to do a I could do. I think before, let's have a look at the current, because we've got the simulation already. Which direction is this current? File, save. Okay, it's doing that way. It shouldn't be doing that way. So what I need to do is minus, there we go. So no current, kind of what we expected. So the voltage drop across this will be opposite. Wait a minute. Is that what I'm expecting? I think so. So that plus that will go to 6.3 volts. Yeah. Got the input voltage, which is 6.3 volts, and then you've got the current as well. So no current, as you can see over here. And then as soon as you hit 0.7 volts on this point, well, around 0.7, you can see the current starts to ramp up, as you pointed out, Thomas. I'm just thinking, what's the best way to explain this to someone who doesn't really understand the question? For me, I'm thinking maybe add more slides to this. So positive voltage. Yeah, no, definitely. I mean, I want to try and get all the concepts out. So it's definitely helpful. I think maybe add another slide in there to see, kind of explain what's happening. I feel like it's probably going to be a 1-minute video, which is fine. I don't really care. If it's 1 minute, it's 1 minute, right? As long as all the topics that need to be covered are covered. That's a good point. So let me add a little note in there. I don't know if that's going into too much detail, but I've never added this much words to my presentations before, but it should be okay. Let me crop that out. That's fine. And this is just the opposite. So it should be fairly easy to imagine, because you've got high voltage on this side and a lower potential on this side. Oh, after this exercise, there's one more question to go on chapter 1, and then we're finally getting on to BJTs, which is going to be really good. I'll be able to build a lot more circuits. I am going to build this circuit as well, so I think that'll be all right. We can do. Constant. Reverse voltage, reverse current. Oh, nice. It's in log. Really easy to understand when it's in log. You got your forward current, forward voltage. See if there's any different data sheets for this port that I can actually, or any port for that matter. It doesn't matter. It doesn't have to be just that port. Another 20 seconds, yeah. It's just what I needed. Bloody hell. Right, I think I'll just draw one myself. So I can actually make it ideal. Third shape. I mean, doing it as a linear line, do you think that's doing a disservice? 0.7 volts. There's a question, what's the typical breakdown voltage on these things? Because this, yeah. This is a 10-fold increase everywhere. So breakdown voltage, let's call it 100 volts. Okay, I think that will cover everything for the actual solution. And then another thing I'm thinking I'll cover in a practical video where I actually just build this circuit and go through what happens. I'll basically add in like temperature effects, how this line moves backwards and forwards with temperature, which is an interesting effect because you can use it to do like temperature sensing and stuff like that. So I don't know, I find it interesting. Do you think this chart needs anything else? Or is it too complicated anyway? You also see it quite often for temperature compensation in feedback circuits. Yep. I know I've used it as like calibrated temperature sensor in the past to sense silicon temperature, which was quite interesting because it's surprisingly linear, the temperature response curve. So that's basically exercise 1.43 done, I think, at this point. I know the next exercise is a little bit harder than this, but as soon as I get through that, we're on to BJTs, which is going to be quite fun, and I can't wait to build those circuits. But I think I'm going to call it a day for today. It's getting a bit late. It's almost 1 o'clock where I am. So yeah, thank you guys for joining. Hopefully you enjoyed this video, and I know KiCAD crashed in the end, so I couldn't finish the things I needed to, but at least we got these slides done for Art of Electronics exercises, which is more important to me anyway. So again, thank you everybody for watching, and yeah, I'll see you next time. Have a good evening or night wherever you are.